From the Library of Congress in Washington, D.C.
I'm Jennifer Harpster. I'm a digital reference specialist with the Science, Technology, and Business Division here at the Library of Congress. I'd like to welcome you to today's program, The Many Colors of the Sun. This program is the second in a series of programs in 2011, presented through a partnership between our division and the NASA Goddard Space Flight Center. And this is our fifth year presenting with Goddard. Our speaker today, Dr. Dean Pesnell, is the project scientist at Goddard's Solar Dynamics Observatory, or SDO. Before his present career as a physicist and investigator of the sun, he first learned about sizzling and fiery hot things as a Burger King French fry specialist. And it's true. He moved from the culinary arts to science, receiving his bachelor degree in physics at the University of Delaware and his doctorate in physics from the University of Florida. Dr. Pesnell has published 80 papers, and probably over 80 papers, I'd imagine by now, in several research areas, including variable stars, the Sun-Earth connection, quantum mechanics, and meteors and planetary atmospheres. As many of you know, space weather and solar flares can affect our technology tools here on Earth, especially our GPS systems and mobile phones. I, for one, when I have problems with my mobile phone or my cable, I will usually blame them on solar flares. For me, it's less stressful to blame things like that on the sun than to call up my cell phone provider. Luckily, we have the SDO folks to study and understand the causes of solar variability and its impacts here on Earth. The SDO is the first mission in NASA's science program called Living with a Star. It is the largest solar observing spacecraft placed in orbit, and the images and data it is sending back are pretty astonishing, as you can see here. From what I have read, the images are 10 times greater in resolution than our high definition televisions. We're very fortunate to have Dr. Pesnell here today to share with us the data and images coming from SDO. So I think we should get started and welcome Dr. Pesnell.
Okay, so the data I'm displaying here is the last 2 days of the sun, or the previous 2 days of the sun, which is a much more positive way to think about it. And it updates every half hour so that you could be 15 minutes to a half hour, maybe 45 minutes behind. But it does it automatically, so you don't have to do any work. And we call this our kiosk movies, and it's turned out to be one of our favorite displays. As a matter of fact, this link right here is one of our, it shows 6 of these panels. I can't do it on my laptop because it doesn't have a screen for it. We encourage you all to use SDO Data. It's a great resource. And I'm just going to talk a little bit about why we need SDO and what we've learned from SDO so far. As soon as my laptop, there we go. Okay. We have studied the sun since we were very young as a civilization. The Babylonians in the upper right-hand corner there, that's a representation of their sun god, and if I'm incorrect, too bad. Okay, it's some god from that area of the world. Maybe not. Maybe it's the Chaldeans. But on the left is a more typical view of the sun that we have today, and in this case, it's also ambiguous. Who here thinks that's a sunrise, and who here thinks it's a sunset? It's very difficult to distinguish between the two. And I don't know, I stole it from the web. But in any event, that's what we think about the sun today. It's a source of weather, it's a source of our timing, our day, our night, our year. We're still there. We still worry about the sun. the sun shows up in art. In the lower left, we have a picture of, we think, a solar eclipse by an artist named Juan Miró. And he had a whole book of these that are really cool to look at, and this is my favorites. On the lower right, we have what are called parhelia. These are sundogs. We'll see a sundog in a picture of SDO's launch, so I thought I'd introduce them now. The sundog is this right here. Where's my, there it is, this thing right here. And then there's another one over here, so they're symmetric, about 23 degrees from the sun. And they're called sundogs. They're just one of the many different kinds of parhelia you can have. And then in the background is probably what started people doing astronomy. That's a solar eclipse. And that's where the moon passes in front of the sun, and because they have the same angular size on the sun, as does your thumb, by the way. If you hold your thumb up like this, it'll also cause an eclipse. Don't practice. It's better to do that on the moon. That's probably why we got astronomy. Because we had these times where for a few minutes the sun was completely taken away, and if your religion is based on the sun and it disappears, you have some issues in your religion. So being able to predict when solar eclipses would happen and whether they're going to happen at this place on the Earth became an essential part of many early astronomers until the 1600s. In the 1600s, they invented a thing called the telescope. Galileo may be credited with that. He did not invent it. Galileo may be credited with discovering sunspots. He did not. But he did leave us a set of beautiful diagrams of the sunspots that he saw. And these are in June of 1613. These are not the first ones, but these are a good set that the Galileo project at Rice University has taken and put into a little animation. And so this is about 2 months worth, about 6 weeks of data taken from the drawings of Galileo. And when you plot them up, you'll notice what happens. The sunspots move. And this is a big issue at the time. Remember, what is the sun? It's a religious symbol. The sun is perfect, except for those eclipses. And now somebody comes along and says there's blotches on the sun. And there was a great deal of work at the time to prove that these were planets orbiting within, between us and the sun. But you don't think that's going to be a planet if you do that for a while. Maybe if you saw one spot, you could say it's a planet. But if you watch them for a while, they change in size, they change in shape, they move across the sun all at the same rate. There's some in the top, there's some in the bottom. So this becomes a conundrum for the astronomers of the time. And they study this, but they don't let anybody really know about it. This is a real issue when we go back in trying to find these early observations. They're often hidden. They're not the kind of things that got publicly accessed at the time because people were basically told they weren't allowed to study it. The big problem is, of course, they didn't disappear. About 30 years later, they stopped being there. That's another thing. All right, the next advance after drawing is they start taking pictures of the sun. Now, the sun is the source of much of our science, just like it's a source of conundra in our religions. It's a source of science because it's the brightest thing in the sky. And if you're building things like telescopes, if you're studying things like quantum mechanics, then the sun is the best place to go look because it's bright and you can see the stuff you want to look at. It's not until the mid-20th century that we build light sources that can compete with the sun in brightness. Here's one of the first photographs ever taken. This is a couple years after the actual first. This is a photograph of the sun, and it's actually in, lousy focus. You would think they could do better, but if you ever go back and see what they're doing, you find out that it's pretty good that they were able to take this picture. And guess what? Sunspots. They're still there. Nowadays, we look at the sun in very narrow filters. We're able to do that because the sun is very bright, and this is a filter of hydrogen. It's in the visible spectrum. We can use this from the ground, and when you look at the sun in hydrogen light, you find out that the sun is nowhere near as simple as it is from your eye, which is a very broad band kind of, it's an RGB kind of sense. These are very narrow colors. It's much narrower than you could see with your eye. And all of a sudden, you start seeing a lot of other stuff. We've been doing this for about 100 years now. These are relatively high quality pictures. You see bright areas on the sun. If you actually look at the sun, that would be where a sunspot is. But the thing that I like is you see these long regions of dark. These are called filaments. And this is another part of the sun's magnetic field that we're going to look at with SDO. Now, that brings us up to about the 1950s. I'm going to skip half a century and just show you what SDO sees. This is the first 7 months of SDO science data, taken about once an hour from May 1st till sometime, I believe it's in early November. This is in 3 bands of light in the extreme ultraviolet. You cannot see this with your eye. That's good. I mean, you could see it with your eye, but your eye would not last. This is the kind of way of radiation that goes in it, and it actually is destructive when it goes into your eye. We use normal CCDs to look at it, but it's not good for organic material. There's 3 of them, and they're all at about 1 million Kelvin, which is about 2 million Fahrenheit in temperature. So when you look at this, you should think, I'm looking at material that's about 2 million Fahrenheit. Pretty hot stuff. When it's dark, that means there's nothing there. And you can just see a dark cap that was on the top of the sun just went away. You can see the dark material coming back around. You see an active region, looks like a spider kind of thing moving across the middle of the screen. You see these dark things. This is the sun at solar minimum. And when we looked at this, we started saying, wow, people really miss, when you just have 0 sunspot number, you can still have a lot of fantastic stuff. Big eruptions coming off the sun. And if I got my talk synced up with the slides, with the movie, I could tell you all the little eruptions that take place. Why do we care? We care because when the sun does something, when the sun burps or hiccups, so here comes something, an ejection coming off the sun, and it moves to the Earth, and it interacts with the Earth. These lines that you see here are the Earth's magnetic field sitting out in space. And as that material moves by that magnetic field, it distorts the magnetic field and changes it. And as a result, it makes the pretty aurora. It's a great little movie. The sun burps, and the Earth gets pretty aurora. And if that was all that was here, I wouldn't be here. Because the only people that would care would be Norwegians and Canadians. And maybe some Alaskans. Okay, so we have more important things to worry about. We have satellites. We have a large infrastructure that depends on radio waves. We have people that every day want to get in an airplane and go over to the Far East. And I forgot my, sorry. And in April of 2011, we had one of those satellites get disturbed by some solar activity, and it started blundering around in the geosynchronous satellite belt. And when we say blunder, we mean blunder. It was just going wherever it felt like. It was moving in one direction. It turned out it just moves in one direction, more or less. But there's other satellites in the way. And as this thing moved around, they had to take all the active satellites and kind of do a dance. So as this moved around the belt, the other satellites had to move in towards us and move out so that that satellite could slide by. Eventually, it went into eclipse on the solar panels, restarted, and now they've recovered it. Now you're on the panel. Would you let them put that back in position and start it back up? I mean, that thing caused angst for 6 months as it blundered around in the geosynchronous belt. And if you were on the panel that was going to vote on giving them their slot back, what would you say? No, I don't want them back. Okay. I work at NASA. We lose satellites. Well, we don't lose satellites. Our satellites are perfect. Other people lose satellites. Galaxy has lost 2. There are 2 up at the top. They lost one back in the late 90s that caused the virtual end of pager service in the United States. Apparently it never recovered. Down below, we have a Canadian satellite called Anik, and then we have the Japanese Adios or Midori, and they were all 4 lost because the sun burped or hiccuped. It did something, and it caused those satellites to get lost. We have in the middle, in those other curves, we have an indicator of how active the sun is. And the stuff where it goes up, that's solar maximum, and when it comes down, that's solar minimum. We're over there on the right-hand side. We just came out of solar minimum. And when we say we're up at around 100, that's what I mean. This isn't actually a sunspot number, but it's the thing that we use for doing satellites. I do work at NASA, and we care about atmospheric drag. We launched, oh, I have to make my economic point. How much are those satellites worth? I have 4 pictures kind of vaguely placed on a page. That's $1 billion that you lose because the sun did something. There's the Hubble Space Telescope and the ISS. They're both in what we call low Earth orbit. They orbit so close to the Earth that what we think is a good vacuum is actually still has enough air to cause drag on the satellite. Drag steals speed. It's just like a brake. It's just not a very good one. The ISS falls towards Earth at about 2 kilometers a month. And so when they send the space shuttle up there, they park the space shuttle on it, and they fire the space shuttle engines to boost it up to a higher altitude. They're going to have to do that because if you work that out, 2 kilometers a month, it only has 200 kilometers to fall. That's 100 months that it has, and they have to keep boosting it up to keep it from falling down. The Hubble was the one that I actually got into this stuff on. They hired me to come in and see whether or not the Hubble was going to fall to ground by today. That was a big concern. Early in 2006, there were some people who said that solar activity for this cycle was going to be of unprecedented levels of activity. If that was true, the Hubble would have re-entered already. Okay, it hasn't. It's still up there. But nonetheless, they had us convene a panel and decide whether or not to send another shuttle mission up to boost the Hubble so that it would stay up another 10 to 20 years. Our conclusion was they only needed to do 1 more reboost, not 2, thereby saving the American taxpayer, my canonical number, $1 billion. Now, I asked at that time for my finder's fee, 0.5%, 0.1%. I'm not particular, you know. I think it was worth it. But they said that I was a NASA civil servant, and that should be reward enough. All right, we'll skip that. Anybody ever been on an airplane? All right. Couple years ago, I got to go to Beijing. Now, when I was young, I got a globe out, and I was told that if I wanted to go from Chicago to Beijing, you put a string at Chicago, and you put a string at Beijing, and you pulled that string tight, and that was the fastest way to go from Chicago to Beijing. I did bring a globe, but I forgot to inflate it. So you'll just have to imagine. If we flatten that trajectory out, that's the blue line, okay? Now, back before 1999, there was this country called, at one point, the Soviet Union, and later Russia. And you'll notice that that blue line goes from Chicago out over Canada, over the Arctic Ocean, and into Russia. At that time, they were shooting planes down if they flew into that space. That's not good for commercial air flight. So they had to fly the red line from Chicago over here to Alaska, and then on down to Kamchatka and Korea, and then eventually into Beijing. If you see that big broad line here, that's my interpretation of the jet stream. I'm a solar physicist. The jet stream to me is a very simple object. It's just an arrow. Okay. But the jet stream represents is several 100-mile-an-hour headwinds. And if you'll notice, that red line flies along the arrow, amazingly enough, for a long part of its trajectory, and that slows the plane down. Basically, the plane is going 500 miles an hour this way, and the wind is going 200 miles an hour that way. The net result is the plane's only going 300 miles an hour. It slows the plane down. It actually made that flight you had to stop in Anchorage to refuel. It took so long. In 1999, United Airlines, who provided these slides, so they're concerned about this a lot, came up with this idea. You fly through the jet streams, go to the North Pole, hang a left, fly south, because there's no other direction from the North Pole, fly south, and go through the jet stream again, and in both times you have avoided headwinds. And it turns out that by flying a longer distance, it's about 40% longer, you can actually save time. That's a great idea. And United, and now others, United started this in the early 2000s, and other airlines have followed suit. And now they actually have all these, if you ignore the blue line and the red line, those were the ones that I drew on the previous one, you have about 5 ways to get up to the North Pole and make your left turn and come down into the other side of the world. Trouble is that yellow circle. If the sun is active, you're not allowed to fly in that yellow circle. You're out of contact with your radio at that point, And solar activity blankets that part of the world, so you can't fly there. And that means you're back to flying either the Great Circle route or the pre-1999. And it costs them, you know, I would like to be able to say it costs $1 billion a flight, but it does. It costs about $250,000 a flight if they have to divert and go down the southern route. So they really want to know what the sun's going to be doing. It's about a 14-hour flight, so they really want to know what the sun's going to be doing between 5 and 10 hours from now. They want a prediction. And that is what they're expecting out of us nowadays in solar physics. There's one last thing I have to talk about. I see solar activity everywhere now. The Big Bang Theory, which I guess isn't surprising, after all, that's a bunch of nerds. You know, it's very realistic except for one part. The beautiful woman that talks to the nerds, that's not realistic at all. I was in graduate school in physics, I know that. In one of the episodes, Sheldon is trying to hide something. He goes out and he comes back and they say, well, he got lost. And they said, well, Sheldon, you always carry your GPS even to walk around the block. And he says, yes, there was a solar flare. And I got lost because it disrupted my GPS. It was great for me. I love these things. The Simpsons has done it. But the thing that has really brought the solar activity, especially the predictions of solar activity, to the forefront is the distortions of next year, 2012. Okay, there are these apocalyptic, end of the world predictions related to a calendar that's so accurate they don't know when it started to within 1,000 years. But next year on December 20th, there's going to be a problem. Okay, they don't know when the calendar started to within 1,000 years, but next year on December 20th, something's going to happen. And so whenever I do an interview now about solar activity, at least one question is going to be related to the apocalyptic visions that people are having for next year. My vision is that this is great. It has brought solar activity to the forefront. It's made a lot of people aware of what's going on. But don't use my data to back up these predictions because it's just not going to go there. So we're in the common literature. We're there. We're on TV. We're in movies. I mean, the movies 2012, or the movie 2012, probably made more money than I will ever have made $1 billion. I mean, I would like to get a share of this pie. They're using my predictions. But I thought I would, since I'm at the Library of Congress, that maybe you guys still read books. And I'll have you know that Mark Twain, you may have heard of him, Samuel Clemens to you, right? He actually has a book about gaming solar activity to make money in grain. Because if the sun changes the weather, if the solar cycle changes the weather, then knowing what the solar cycle is doing means I could tell you what the wheat price is going to be next year. And more importantly, if I can control it. And he's going to sell shares in a company to control the sun, to control the weather, to control the wheat prices. So these literary references are all over. They all want predictions. That United pilot wants to know what's going to happen today, hours. They actually get reports that in part our data helps support, done by a government agency in Boulder, Colorado, called SwiftSea. And they produce these alerts that the pilots need to go over the poles. The guys that do satellites, they want to know what's going to happen for the next couple of months so they can plan out. Do I have to worry about things? And the solar cycle guys, they want things that go forever. They want me to tell them what the solar cycle did back when they were building Stonehenge so that they can find out whether or not there's some alignment at Stonehenge related to solar activity. That's kind of fun. That's not really what I care about. I care about the Hubble and my finder speed. Okay, we don't use them anymore. We use computer models. This is a computer model. This is what we would like to understand. Those are the sunspots on the sun, and then we're going to split the sun apart and show you what the sunspots come from, the solar magnetic field. Those lines are kind of hard to explain, but if you see a lot of them close together, that's a strong field. If you don't see very many close together, it's a weak field. That's all you really need to know. And you'll notice that the strong field is virtually all down deep inside the sun. Guess what? We can't see there very easily. We see the stuff on the outside easily. But that's just like the tip of the iceberg for what's going on inside the sun. And this is one of the better models for the solar magnetic field. We call it the solar dynamo, but it's one of the better models, and not just because I helped. Okay, what are we going to use? We need data. This is like weather forecasting all of a sudden. We need data because we need to know what the sun is doing now, we need to know what it did before, and we need to make a model, predict what's happening, and then get data to come back and tell us what it did. And then you correct your model and try again. The weather forecasters have been doing that for 60 years with stunningly accurate results. That usually works. And we would like to emulate the weathermen and give ourselves career-long work to do this. SDO was launched on February 10th or 11th, 2010 from the Kennedy Space Flight Center. You guys were up here in 4 feet of snow. We were down in Florida, and boy, was it cold. SDO is now in an inclined geosynchronous orbit at about the longitude of New Mexico, and we are in continuous contact with the spacecraft so that the data we get is coming down constantly. That's why we can do that kiosk mode movie and tell you the data is about a half hour old, because we get the data every 3 minutes sent off to the right place. And it takes a while to propagate through all the data system. We have about a 5-year mission. We at least 10 years from all the other issues we have, and 900 years of propellant. So we're in good shape for the propellant. Okay, we had a great launch. You wish you were there, because I didn't have to shovel any snow. And these are images from SDO. This was not made before launch. This is made after launch. It took off. That's our Atlas V. We brought a little model of it that we had out front. And as it lifted off, we saw one of those sundogs. I was lifting my binoculars to follow the trajectory, and a sundog came into view. And you see those ripples going away? The sundog disappeared as a result of those ripples. And it's probably the first time in history, and that's not just me now. I mean, we actually did ask some atmospheric ice halo experts, parhelia perfectionists. And that's probably the first time we've seen one of those things change as a result of something man did. So it was kind of cool, and I had a student that got to work on it, and that was a lot of fun. But more importantly, we started opening our instruments. This is the first day of observations from what we call the AIA instrument, the Atmospheric Imaging Assembly. And you'll notice that nothing exceptional happened. Okay, all we had was this incredibly beautiful erupting prominence. And as we pull back from it, you'll see, and the lights that they have on, so that people in the webcast can see me. The lights are denying you the full impact of the image that you have. But that was our first light. It's only gotten better since. But I need to talk for just a few minutes about how we're showing you the data. We don't show you things in false color. We just make it up. I mean, we're lying to you on these colors. They have nothing to do with the data that we show you. But they are coded so that when we see an image, we kind of know what it is. I mean, that's the only important thing, is that when we see an image, we can say that's an AIA 304 or AIA 193. We're not looking to do any other representation. This isn't like trying to do true color on Mars or something like that. We're just lying to you. And the other thing we're going to do is we're going to show you a lot of stop action movies. Because what we do is we take pictures fairly quickly. AIA takes a picture in each color every 12 seconds. And then we basically take them and show them to you as a flip show, and it looks like an animation. They're stop action. We're being open and above board with this. We just do it because it looks cool. And it's how your eye is a great thing to look at these movies, because it sees things. It sees things in the movies very, very readily. So the goal is that you get to watch them pick stuff out. Let's go through our false colors. That looks like the sun, right? All right, I'm lying to you. That should be blue. Okay, this image actually is lying. This is a false color. It's taking it blue, but they make it yellow because that's what everybody expects. This is taking it for a reason. You'll see those two dark spots up at the top in the yellow. Now they're still dark, but you'll notice that some other stuff showed up. There's a little bit cooler temperature. I have the temperature down in the lower right, so I forget to tell you what it is. I can be reminded. It's a little warmer. You're seeing some bright stuff. Now you're starting to see the old man in the sun. Okay, he's got his eyes up top, his mouth down below. This is helium. This is our favorite color. This is my favorite one. And then we move into even hotter temperatures. Here are those things that I said was about 1 million, 0.6, 1, and 2 million Kelvin. And that's, you multiply that by 1.8 for Fahrenheit. We move off even hotter. And then our hottest channel is 10 million Kelvin. This is pretty dang hot stuff. What's that? Wait a minute, it's not color. Well, yeah, it is. It's black and white. Okay, we could have done this back in the 50s. This is what we call the magnetic field of the sun. And in this case, the magnetic field of the sun, where it's white, is pointing towards you, and where it's black, it's pointing away from you. Magnetic field has a direction. We have to keep track of that. You'll notice that the magnetic field up around those places that were dark, there we are, right around here, you notice that there's black and white next to each other. Over here, there's black and white next to each other. And down here, there's this long thing of black and a long thing of white. They're not kind of mixed up. They're kind of separated. In the south, that's the southern hemisphere, and it's just the way the south has been as we came out of solar minimum. The north saw the development of sunspots, and the south held up for quite a while. I made this last week. We've been working on these dual movies. I like the little spray that happens over in the upper right-hand corner. If you watch over here, you'll see a spray. You saw the spray there. That's just material being ejected from the sun, just being pushed off. Not quite as exciting as a prominence eruption, but still it's material going off. And then I have it over on this side. If you look at the same region, you can almost look like lightning going from here to here. You see the loops. They're almost like lightning joining those two pieces of the sun. Now, we're used to things being joined together. With AIA, we're starting to, and the SDO data, we're starting to see that those joins happen over much larger parts of the sun than we realized would be normal. We expected them in some cases, but we're starting to see that the sun in one part over here is actually joined to here and then over to here. So we're seeing the sun kind of has all these little islands of magnetic field, but those islands are joined by these loops that go between them. You did mention the HGTV. So here is our attempt to show you, actually you're probably all American tax dollars. This is your tax dollars at work, and so it's always good to show you what you're getting for your money. Over here, you'll notice that I have a young person doing my web stuff. That's his standard TV. Long time ago, that's what TV looked like. And then we have one of the first long-term missions of the study of the sun called SOHO. Still up there. It's been up there almost 16 years now. And that was what we call 1,000 pixels by 1,000 pixels. And then we have your standard 1080 high-definition television. It's 1,080 pixels this way, 1920 that way. Stereo, another satellite, is 2 by 2,000 by 2,000. And then we're 4,000 by 4,000. We're the biggest. Therefore, we're the best. The more important thing is that we take data very quickly. We picked an orbit that we can get data down easily. And so we take one of those pictures every 12 seconds. Stereo takes one every several minutes. SOHO took one every 12 minutes. And actually, in that wavelength of helium there, it took one every 6 hours. So we are able to see things happening in time that was simply impossible with the earlier data sets. Okay, like this flare right here. That's our first XClass flare. It's just like a proud papa. X2.2 happened on Valentine's Day, our time, a little early in the morning on February 15th in the UT clock. The flare is the little bright spot in the middle. Contrary to all of broadcasters in the United States, the XClass flare is not the X. Okay, that's just that's a problem with the telescope. There's some reflections in the telescope. It's the bright thing at the center that's the actual flare. Who cares? You do. That flare, now you can't see it. Yeah, the contrast. So imagine. The flare goes off, and a little puff, almost a smoke ring, comes out from the sun. Why do we care? If a puff comes off the sun and we see it as a little thing going off to the side, like a stream of water, it's not going to hit us. If we see it streaming off the other side, it's not going to hit us. If we see it looking like it's a round circle, where's it going? You're looking right down the pipe, and that is coming, and it's going to hit the Earth. So this flare goes off Monday night, Valentine's Day, and we're all sitting in our homes, texting and tweeting and all this other stuff all about this flare because we thought it was pretty cool. Our first XClass flare. And then the CME is seen to be coming towards Earth. It's called a halo CME because we see it looks like a halo around the sun. Well, remember those 2012 guys. Big flare, CME, hits the Earth, end of the world. By Friday, they're all disappointed. The world didn't end. And I think they were actually disappointed. Which, in one case, I asked an interviewer, which would be worse? The world ending or not? And I think. So I have some mixed feelings about all this kind of stuff, where people take these observations and tend to overinterpret them in terms of some other prophecies or thought stuff. But unfortunately, this one, or fortunately, well, it depends. This one missed. I call it a curveball, high and inside. Okay, it went behind us and out a little bit above the Earth. So as it came around, it slowed down a little bit too much. Earth was able to move out of the way, and it went right on by us. It did cause some significant aurora. Remember those? It did cause some pretty beautiful aurora, but very little else. This, on the other hand, excuse me, I clicked through twice. Let me go back. That one's great. I mean, if you want to study the sun, this is the kind of stuff you want to see. Okay, remember, this is a stop action flick. It goes to, it rewinds. All that stuff falls back down onto the ground, or the surface of the sun. And then it lets it go again. I call that the Trebuchet prominence eruption. Because it looks like a trebuchet. It's even the right color, right? It's throwing pumpkins.
From Delaware.
Okay, there it goes again. We watched this movie for over an hour when this happened. I mean, Barbara Thompson, the lady that made this movie, made like 20 versions of it, and we're watching them all, and it illustrates so much about solar physics in just this one movie. The rapid motion over there, the billowing of this material as it moves to the left, and then finally the material slows down enough that it says, oh my God, there's a magnetic field, and it starts moving in straight lines. So as long as it's kind of moving in those billows, it's kind of forgotten there's a magnetic field, and then all of a sudden it slows down just enough that it feels the magnetic field, and it falls back down onto the surface. It's just a marvelous example of an eruptive prominence. And the fact that it kind of looks like a trebuchet is just fun because I build them with my son. That's not him. Okay, we have another instrument. We don't just get beautiful images. We actually do get scientific data from this satellite. And one set of data is called Dopplergrams. These are waves moving across the surface of the sun. We see them in velocity. You may all have done the Doppler experiments where you had to go out and listen to a train go by, and the train pitch goes up as it comes towards you and goes down. By the way, when you do that, you stand off the track. You don't have to stand directly in front of it. That's a way to ruin the experiment. We do that over the disk of the sun, and we see these waves rippling across the sun. We see a lot of other stuff too. We're going to talk only about the waves. And the guy that does this, Phil Scher, has assured me that if you've seen one Dopplergram, you've seen them all. You've seen 2 days worth. Are you done? Okay. But by the way, it's not the data. It's what we can do with that data that it makes this almost a magical instrument. And I'm going to give 2 examples. One is we can see all the way through to the other side of the sun. The sound wave goes to the other side of the sun and comes back. And because of that, it's affected by what happens on the other side. And if you do the analysis correctly, and we're almost ready to prove it, you can actually see sunspots on the far side of the sun. That's pretty cool. Remember prediction. The guys that do satellites, they want to know what's going to happen in a couple of weeks. Well, guess what? The sun takes 27 days to rotate. If I can see something on the other side of the sun, that's giving me a week to 2 weeks warning that something's coming around to the other side of the sun. This has been these far side images have been accepted by the predictive community for about 10 years now. They're one of the coolest things that come out of SOHO. We've learned how to do it better. That's what scientists do. You see great stuff, and we just try and make it better and better. And these are just simply getting better. The HMI data is the better data, and also the algorithms have been improved over the last 10 years. To where we're able to look on the Earth side and see things, and look at the far side, and in this case, see nothing. Isn't that great? Okay, if I want to do solar cycle prediction, I got to see that magnetic field that was deep, deep down inside the sun. And I can use these waves to do the same thing. Those waves dive down into the sun, and just like they're affected by the stuff on the far side of the sun, they're affected by what happens when they go deep down into the sun, and I can develop, these are kind of rivers in the sun. They would actually, the sun looks more like Jupiter than it does like the Earth. It has bands that move around it. And you take those bands and look at them, and some are moving a little bit faster. That's what yellow means. And some are moving a little bit slower. That's whatever that color is. I didn't do this plot. It's a pretty ugly color scheme. That band moving down is the thing that we like. This thing started here, right here, and moved down. And right along there, if you plotted the sunspots that showed up in solar cycle 23, the one that just ended, they would have been at or above that boundary. And it's an amazing thing to look at that and say that river inside the sun knows something about sunspots. Actually, it's probably the other way around. The sunspots know where to erupt because where that river is happening. Here is cycle 24 showing up here in around 2002 or so. Solar cycle 24 actually showed up, and regardless of what anybody in the prophecy world thought, we saw this band coming down, and and all of a sudden they started, when it passed, I can't see my thing, there it is. Right around here, it passed about 35 degrees north latitude, and sunspots appeared. We don't know if that's a correlation. It happened twice. You know, that's the way it is with correlations. They happen. You don't know whether to believe it. But that's when we knew cycle 24 was going to show up. We saw this band coming down, and regardless of what anybody else said, we could look at that and say, solar cycle 24 is here, and this seems to support it being weak as well. Okay, that magnetic field thing. The research instrument on SDO is actually studying the magnetic field, but the direction as well as that black or white. Black and white just meant it was towards us or away from us. We actually want to know the slant angle. We want to know how much of it is pointed this way, not just this way. We want to know how much is that way. And so this is one of the early examples. This is still a research project. It hasn't been completed yet. And at each point, they've drawn a little line that represents the magnetic field direction and strength. The length is the strength, and the angle is the direction. And at this point, they're cool looking hedgehog diagrams. They look like moles or something running around in your yard. There is actually a lot of information in here. In the next 10 years, we're going to see this become what the wave data was for SOHO. We're not quite sure what we're going to do with it, but we know we're going to be able to do some great stuff with it. All right, and just to show you some other thing, oh man, I wish you could all crowd around here. This is magnetic field. You can see the white. That's magnetic field pointing towards you, bubbling up out of the sun. And this is how a sunspot forms, or an active region. It just shows up. It boils up from inside. It doesn't magically appear. We can watch them show up. And we have some early evidence that we can see things happening before they show up. So once again, that's a prediction. Get about a day to several days warning that an active region is about to appear. That's another research project. It's not done yet, but we're hoping that over the next 5 years or so, we'll get the data to understand that better. So we'll be able to do prediction. All right. You saw that over the course of 400 years, we went from people looking at the sun through telescopes and drawing things on paper to some really exceptionally beautiful images of the sun in wavelengths that Galileo could not have imagined. And the challenge that I think I gave this talk, I gave an early version of this talk last week with kids in the room. And the challenge to them is, what are you going to look at the sun as? I mean, this This is what you're going to grow up looking at the sun like. What are you going to be doing in the next solar? What's solar cycle 25 going to be studied with? Because we're doing a great job now, but we've been doing a great job in every solar cycle so far. We've pushed the limit of technology in every solar cycle. SOHO pushed the limit for space-based technology. Before that, we had YOCO. We've had satellites. We've had ground-based. They've always pushed the limit because this is the sun. This is where you can do it. You got plenty of signal. What are you going to look at the sun like in solar cycle 25? And with that, join us. It's your data. I mean, you probably don't want it all. It's about a petabyte a year, a terabyte and a half a day of download, which decompresses to somewhere around 2 to 3 terabytes a day in data. You don't want it all, but we try and make it available to you so you can look at it. And the data, and I'm going to go back to that page in a minute for questions. Come to our website. That's the sdo.gsfc.nasa.gov. We have some cool ways to look at all the different kinds of data. We have I've been fortunate to bring on board the SDO project, what we call an education and public outreach team that's much younger than me. That's not hard to do. I was born at the dawn of the space age. They have grown up with computers, and they think that tweeting and all these other social media is the way to be, and they indeed participate in tweet ups. We're having one on Saturday, and we have a Facebook presence, and it's all an attempt to get people out there aware of solar activity and how SDO data can be used, played with, people doing art contests with it. So, join the fun. It's a great data set. And thank you very much.
So we have about 10 minutes for questions. I'm sure there are questions. I'll start in the back and work up. Yeah.
Hi, I work in geography and maps, so a lot of this is quite relevant. However, I'm not an expert, so please pardon if I'm not asking the question the best way. But could you talk to us more about how you think your predictions will improve, whether it has to do with the mapping and the algorithms and the just overall precision? How do you think that's going to improve over time?
Okay, so I'm going to repeat your question, and that's the one I'm actually going to answer. Okay. How does if it's not the right question, we'll have to iterate.
Okay.
So how does analyzing SEO data help us with our mapping algorithms? And actually, that's a critical point to us. We don't have continents. We don't have a fixed point on the sun at all. We kind of have to work with this rotating body that rotates faster at the equator and slower at the poles, and not all the time. So we have real problems with mapping, and even my graduate students who attempt to map features on the sun are having issues because they're off by a couple of pixels that cause them to be off. Instead of 1%, it was 2% in the number they were trying to do. So they're off 100% because of the inability to map the sun accurately. So I think that we do worry about the projection and mapping and putting coordinates on the sun on all the time. That's a major issue. I don't know whether our flexible coordinate system can be adapted to what you need on the Earth, but certainly the people on SDO are aware of geographic mapping conventions, and what we do gets fed back in to the there's several standards conventions that worry about mapping conventions, and the solar people have over the last 10 years become one of those standards committees in an attempt to get us a standard coordinate system on the sun. It has not been completely successful. We're off by degrees in both directions on a regular basis, but we're much better than we used to be. So I think it will help a lot, but the iteration, it's an iterative process that would take place over the next couple of years.
As a layman, when you're looking at these movies and photographs, is there any consistency in the colors represented? Like, if I'm looking at a green, movie or photograph of the sun, does that indicate helium? Is there any consistency within SDO or within people who scientifically take pictures of the sun in general, or is it pretty much random?
Okay, so the question is, do we lie to you the same all the time? Okay, you would like to know whether our colors are always the same colors. And no. As a matter of fact, people argue. If you want to get people in a science conference to argue with each other, just argue whether that's the right color. Okay, that was blue in Soho.
Oh,
Okay, and we actually in our helium line, the one that the Trebuchet prominence was shown in, we like that orange, and the people that actually produce the data make it a much darker red. You can barely see. You saw that when I did the comparative slide. That's one of the other color tables. So there tends not to be a consistency because people look at different things. So somebody that wants to look at something in the middle of the sun will want a different color table than somebody who wants to look around the edge of the sun. Things are dimmer at the edge than they are in the middle, and so they'll do a different color table to emphasize that. We do attempt to maintain consistency, but it's a scientific mission, and the people that take the data don't actually get it with a color table. They get a black and white image and have to put a color table on it, and at that point, you've lost any consistency. But we attempt to, with the data that comes from our website, we are trying to keep it all the same color table to avoid that confusion. And we are attempting to get people to use the same color table, but then somebody, as soon as everybody says, okay, we agree, then somebody will say, yes, but I like this one to be blue. So you lose at that point. There's always going to be differences. That's why it's important that you look in the lower left-hand corner, and that tells you what the band is. This is the 171 channel. So we have 304, 171, 211, 193. And by knowing what that channel is, you know what data you're looking at.
Yeah, so given that there is some correlation between the solar activity and also seismic activity, although that doesn't prove a cause, given the current earthquake that occurred in Japan, shouldn't there be a discussion around perhaps what is causing some of this activity? Perhaps it lies in, say, cosmic ray flux or something or other. Shouldn't this be something to look into, given some of this activity that's going on, these natural disasters, rather than sort of the current media hysteria around the one nuclear plant?
Okay, so I'm going to interpret that question as, is there a correlation between solar activity and earthquakes here on Earth? That correlation is much disputed. There are people that say it's true. There are other people that say it's not. I am not an expert on.
I was actually saying, shouldn't we investigate?
I'm almost there.
Yeah.
Okay. Feel free. Okay. I mean, you think you have a legitimate scientific question. This is the United States. Here's the data. The earthquake data is available as freely as the solar activity data. There's nothing wrong with attempting to study that. This is a big subject, especially in Eastern Europe and Greece, is whether or not there's a relationship between solar activity and earthquake activity. The work I have seen, it has been spotty, and the data tends to be cleaned a lot.
yeah.
So where you take, where there's large, so let's say I don't have a causal response, okay? But let's just say if there's an X3 flare, we tend to have a magnitude 7 earthquake within 2 days. Okay, what they do, and I've watched the papers, they just take out the times it doesn't work. And so it becomes a very poor prediction at that time, because you'll have a lot of flares where there isn't an earthquake, and they just don't include that data because, well, I didn't have an earthquake to put it in. So it's one of the areas where correlation is a difficult, correlation versus causation becomes a problem. And having actually studied earthquake prediction, that's solar activity is not the most important thing in earthquake prediction. But once again, feel free. The data is available, and you can suggest it to other people as well. But there's a lot of interest in whether or not that is true.
Don't work. Oh, wait. That's right. Yeah, I'll try to.
Okay. May I ask 3 quick, easy questions about SDO?
3?
They're easy.
There are other people in the room.
try one?
Yeah, go ahead.
Are the sensors going to have to be baked off like they do on Soho?
Okay, so you asked whether the sensors have to be baked out. The goal was to not bake them out. However, there appears to be contamination, and so we will be baking them out. Probably not as much as on Soho. We were evidently a little bit better at contamination control, but there appears to be water inside the telescopes, and that forms ice on the detectors. They're held at minus 100 Celsius. That forms ice, and over time you have to just warm them up and push the ice off. And it looks like we'll have to do it every 6 months or so, but not for as long as they did on Soho.
Okay.
How about someone would come back?
When you see something, an emission from the sun, remind me, how long does it take before it actually impacts the Earth?
How long does it take light to get from the sun to the Earth?
Well, no,
Eight.
An emission.
I'll get there. Light. A flare is a flash of light. That's all a flare is a big flash of light. 8 minutes. Within 20%. It takes the material that comes off the sun as actual particles, mostly hydrogen, some helium, and a bunch of everything else. And that travels at around 1 million miles an hour. How far is the Earth from the sun? 93 million miles. Takes 93 hours on average to get here. That's about 4 days. Yeah, 4 days. The stuff that comes off can be faster. It can be here as rapidly as about an hour, which means it's really moving fast when it leaves the sun, a lot faster than 1 million miles an hour. And it can also take slower because of the path it has to take is not necessarily straight. It can be quite curved, and so it can take considerably longer. The ones that are dangerous are the ones that get here fast. We've seen times, there was an episode in 2006 where the particles got here about 90 minutes after the flare. So that's the trigger. You see a flare, that's 8 minutes, the event happened 8 minutes ago, and now you want to know how fast the particles are going to be here. If they're there within hours, you know that was a fast, very energetic particle event. And that one wiped out GPS over the United States for 8 hours. It was a good event. I use paper maps.
Stephanie, the earthquakes at Central were actually caused by the supermoons.
Oh, we're at the supermoons.
Supermoons. I'm sorry, the earthquakes being caused by the supermoons does not parse. I don't know what the supermoon is, but
Oh, that's when the moon is really close to the Earth, and on Saturday it's going to be the closest it's been since 1993. And a lot of people were saying, well, when Katrina happened, it was within close to a supermoon.
Close.
And now that we had Japan,
Right.
that was the supermoon. So leave the sun out of it.
I saw an excellent lecture on earthquake prediction by a man who, at the AGU meeting, we go to these meetings, and they had a half-hour talk, and the guy didn't show up. And rather than get off time, he said, okay, I'll tell you what, I'll just get up and give you an extemporaneous talk on earthquake prediction. It was probably the best talk I've ever seen on earthquake prediction. And there are attempts to do it. These guys really work at it, and they have all the title stuff. They do. And they're just as bad at it as anybody else. It's very difficult to do, because to a first order, what you're looking at is somebody slipping on the floor. Okay? Two things are pushing like this, and eventually they go like that. And you're trying to predict when that happens. It may be like this in California. I believe it's a subduction zone near Japan, so the thing went like that, went down into the Earth. You're just trying to predict when that slip is going to occur. And they really work at it. They get paid. They would get paid a lot of money if they could do it. But I'm sure that the tidal forces from the moon may be a part of that, and I would believe that more than I would solar activity.
So we have a couple more. We'll come back to you. Oh, go ahead, sir.
That's okay. You commented on Big Bang Theory, and I just wanted to know which was your favorite nerd and who is which one is the most realistic? Howard? Leonard?
Okay, the best actor is Raj,
Right.
because he's the one that always has to react in a way that's consistent with whatever anybody else just did. So I think he's the best actor. Sheldon is just like, I can't use the language here. One of the professors that I did not have to take a class with, but was at the University of Florida where I was a graduate student. That Sheldon, you could replace that guy with Sheldon and know what it was like to interact with him.
I knew one in Hartford.
You know, Leonard, of course, because he's the only one that has glasses like they should. So Leonard's my favorite, but that's only because he has glasses. Also, he got to date a beautiful woman, and you know, that was like
Wasn't realistic.
yeah, but that was just a dream of mine when I was at graduate school.
Raj's sister.
Yeah, but that's just because the show has actually lasted more than 2 seasons. Yeah.
What sort of orbit is SDO in, and are the sensors gonna white out when a flare hits them, like Soho did?
Okay, so what orbit is SDO in, and what will happen to the sensors during a particle storm?
Yes.
Okay, it's in an inclined geosynchronous orbit.
Okay.
So that means it has a 1-day period. It appears to stay at roughly the same longitude, but it's inclined, so it actually tracks out a figure 8 over the ground station. So with the ground station antenna, it doesn't just point, it has to kind of point and, yeah, it has an analemma shape that it has to trace out. We did that because we're cheap. Okay, the geostationary orbits are expensive. You have to pay for them. And so rather than take one, we just go through it twice a day. So we essentially occupy it and didn't have to pay. The sensors will white out. You don't see that because that's been removed. We take out the particle hits. Before the data shows up, the particle hits are removed. They probably won't be as bad as SOHO because the instruments, in this case, the one on SOHO is actually open. So the particles can stream right down to the CCD. All our instruments have some kind of metal between the solar particles and the CCD. It's hitting the CCD that's bad. And so we surrounded them with metal, learning from SOHO, trying to minimize those hits. But if a big storm comes, we'll see the same kind of patterns. And then we have built a very expensive particle detector.
Thank you, everyone. And there's some NASA swag out. So we have to pay somebody for orbits in certain areas?
You have to rent them.
This has been a presentation of the Library of Congress. Visit us at loc.gov.